Okay, so now we're ready for hydration part 2. And this is the hydroboration-oxidation of alkynes. So we've got our borohydride, and if you'll recall, this is going to give us an anti-McConaughey. So instead of putting the hydroxy on the substituted carbon, it's going to put it on the non-substituted carbon. It's going to put it on the end here. So here's our new hydrogen that we added. Here's the R group that was already there. And here's our new hydroxy group. And it's in the anti-McConaughey. But if you'll look, we have made an Enol again. This is not stable, and it will form an aldehyde. Okay, you can't isolate this enol form. It's just not stable enough to isolate. And what we have here, as we go from enol to aldehyde, is a base catalyzed tautomerization. And I'm going to draw that out for you. Okay, so I've drawn the enol. You'll see that it's got a double bond next to a hydroxy group. And what's going to happen is this is our base, and it's going to come in and steal the proton there. And the electrons that are attaching the proton to the oxygen will now go and live on the oxygen. So that gives us this first form here. We've got a negative charge. We've got a negative charge here on our oxygen, and this has a resonance structure because these extra electrons can come down here to make a double bond and push these electrons to live on that carbon. And we get extra charge there and a negative on being borne by this carbon right there. When it's in this state, these electrons here can pull off a proton from water. That'll regenerate our base, so we can restart the reaction, and we end up with an aldehyde. We end up with here, proton here. Here's the one we just took off of water. Here's our original R group, and this is an aldehyde. Now, to prevent a second addition, sterically hindered dialkyl borane is used. So you'll see R2BH as the abbreviation. The actual chemical names are diacylamyl borane and 9-BBN. My little note here is that a terminal alkyne will give you an aldehyde through this reaction. So when you're doing synthesis and you know you need an aldehyde, this is one of the ways you can get it. Okay, so if we have this compound and we treat it with the sterically hindered diacyl borane, remember we also need to use the peroxide and sodium hydroxide, just like we did with the boron dihydride. We've got 1, 2, 3, 4 carbons. We're going to end up with a 4-carbon structure, and it will be an aldehyde. So draw the major product for each of the following. So here our initial product will look like this. We've got 1, 2, 3 carbons, so we'll go 1, 2, 3. This is going to add to the less substituted carbon, so that's what we get. But this is going to be an enol, and it's not going to be stable. And our final product will be an aldehyde. 1, 2, 3. And here, again, we've got 1, 2, 3, 4 carbons. Here's our 4 carbons. We're going to add a hydroxy to the less substituted position, and that will be an enol. On the third carbon, 1, 2, 3, we're going to have 2 methyl groups. This will not be isolated, but instead we'll get, here's our 4 carbons in a row, and here's our aldehyde. We have to put our methyl groups on that third carbon. It's very helpful to number your carbons and then number them over here to make sure that you get the right number. Okay, so when we do synthesis, a lot of times we want to work backwards. So if we were going to make these compounds, what kind of alkyne would we start with? So compound 1 here is an aldehyde. And if we have a terminal alkyne, we can make an aldehyde. So let's start with a terminal alkyne. We've got 1, 2, 3, 4, 5, 6 carbons. So we want to have the same number of carbons. 1, 2, 3, 4, 5, 6. 3, 4, 5, 6. And on this carbon, the 5th carbon, we need to have a methyl group. And that should give us, if it's treated with diborohydride, will give us the aldehyde. This one's ketone. And we start with this compound. It will give us this ketone. Because it's symmetrical, it won't matter whether we add to this carbon or to this carbon. We'll still get the same thing. 1, 2, 3 carbons. 1, 2, 3 carbons. 1, 2, 3. And it's 1, 2, 3 from the other direction as well. So we can control where our carboxy goes. If we use an acid catalyzed procedure, it will go on the more substituted carbon, and we'll end up with something that looks like this, which we're going to call a methyl ketone. Because it's a ketone and it's got this methyl group on it. If we do the borohydride oxidation step, then we will add our hydroxy to the less substituted carbon, and we end up with, let's see, this, which is going to be an aldehyde. So you can control what you're going to get out of your reaction by being very careful about your reagents. So let's identify the reagents that you would use to achieve the following. So the first one here, we've made a ketone. And so we're using, this is an acid catalyzed hydration in the presence of mercury sulfate. The second one is going to be antimaconicoff, and it's a hydroboration-oxidation. So we'll be using this sterically hindered hydrogen boride, and then peroxide and sodium hydroxide. And that is the end of hydration.